Okay, so the idea of heat capacity, how do we define heat capacity in the first place? Like, what is heat capacity?
The amount of temperature, or yeah, the amount of energy it takes to warm something up by a degree.
Yeah, and specifically the amount of heat, because the energy transfer could be heat or work or a combination of those. Heat capacity is specifically talking about heat required per degree of temperature change. The heat required per degree of temperature change. So we can define that as a ratio. Heat capacity is defined as heat over delta temperature. That is how much heat you add divided by how much the temperature changes as a result. Well, I should say how much heat you add or remove. Because if you remove heat, Q is negative, but also that decreases the temperature, so delta T will be negative, which means heat capacity should always be positive. So this varies depending on the circumstances, because if you hold if you have like a gas that's at constant volume, the volume is not allowed to change at all, then certain behaviors occur. Whereas if you do allow the volume to change, then the behavior is going to be different. For example, let's say you've got a gas in a container with a piston that can move up and down. If you add heat to that gas, what's going to happen?
It's going to bring that piston up. It'll expand in volume.
Exactly. The gas expands in volume, raising the piston. And by raising the piston, that piston, let's say it's a heavy piston, is going up. So what type of energy is changing there?
Is that work? Because
yeah,
it has something to do with
we could treat that as, sorry, what was that?
I said work.
Yeah, we could treat that as work leaving the system, which means heat is not the only thing involved. You could also treat that if you've got an object with mass that's moving upwards, what type of energy is changing? Yeah, potential energy, specifically potential energy of gravity. So if you have a gas in a container with a piston, let's say a weighted piston, you add heat to it, you're raising the temperature of the gas, so that is increasing thermal energy, but you're also lifting the piston as the gas expands. So you're applying heat to the system, increasing thermal energy and increasing potential energy of gravity, which means not all the heat you added goes into raising the temperature, some of it goes into lifting the piston instead. So if the gas is allowed to change volume, this is less efficient. Not all the heat you add goes directly to thermal energy. But if we don't allow the volume to change, if we have a rigid walled container with either no piston or a piston that's locked in place, if we assume the volume does not change, and also assuming there's no phase change, then all the energy you add goes directly into thermal energy. So in that case, if the volume is constant, then all the heat goes directly into raising the thermal energy and therefore the temperature. So we can say that heat is delta E thermal. Whereas in other cases, delta E thermal would be heat plus work. But if we assume the volume does not change, if we assume this is a rigid walled box full of gas, then there is no work done because nothing's really moving. We're not expanding or contracting the walls. So in that constant volume case, we can assume heat is delta E thermal and say the heat capacity at constant volume, usually written as C sub V, is delta E thermal over delta temperature. And this is usually the way we tend to think of heat capacity in the first place, delta E thermal over delta temperature, because then you get delta E thermal equals heat capacity at constant volume times delta temperature. And this relationship is actually true no matter what the process is, whether the volume is changing or not. The change in thermal energy is always heat capacity at constant volume times delta temperature. So the relationship between delta E thermal and delta temperature is the constant volume heat capacity. The relationship between heat and delta temperature is heat capacity depending on the process. So it might be constant volume or constant pressure heat capacity. But if you're talking about delta E thermal, you always use constant volume heat capacity because that assumes that it's just delta E thermal, not just the heat. But for now, let's assume it's constant volume. Any questions on that so far? So if we want to get more detail on what heat capacity is, we're going to need some other formula for delta E thermal. And we can get that based on the whole idea of number of modes. If you look at each individual mode, the microscopic perspective, if we consider the individual modes, what's the energy of one mode? Or how would we calculate how much energy one mode has? If you want to know the energy of just one mode, how would you calculate that? Or what does it depend on? One mode would just be 1/2 kBT. 3/2 kBT would be the energy of three modes. For instance, the 3 kinetic energy modes of one molecule. But any one mode is just half of Boltzmann's constant times the temperature. This is, I mean, the main idea is that the energy per mode depends only on temperature. So energy per mode should be some constant times temperature. That constant turns out to be half of Boltzmann's constant. If we wanted to scale that up to one molecule or one atom, whatever the particle is, we can take that energy per mode and multiply it by the number of modes in the molecule. And I'm just going to write number of modes here. Keep in mind that's number of modes per molecule. So for instance, if it's monoatomic, that would just be 3. If it's diatomic with all modes active, that would be 7, or maybe 5 if the vibrational modes are frozen out. Or if it's a solid, you would assume it's 6 modes per atom. But however many modes the molecule has, that number of modes times the energy per mode is the energy of that whole molecule. And you could almost think of this as like a unit conversion thing. We have the kB/2 times temperature is the energy per mode. And we're multiplying that by number of modes per molecule. If you multiply energy per mode times modes per molecule, what's going to happen?
Modes cancels out.
Yeah, modes and modes cancels out. We just get energy per molecule, which is exactly what we're looking for here. Or if we want to scale that up, let's say we're talking about not one molecule, but 1 mole of molecules. If we know the energy per molecule, how do we scale that up to an entire mole?
Use Avogadro.
Oh yeah.
Yeah, the number of molecules in 1 mole. We can take this exact same value and multiply by number of molecules in 1 mole, which is just Avogadro's number. So you could think of that in terms of, if we want to look at this in terms of units, we've got energy per mode times modes per molecule. And then Avogadro's number is just molecules per mole. So modes and modes cancel out, molecules and molecules cancel out. We're left with energy per mole. Any questions on that so far? And also a very convenient shortcut. We've got Boltzmann's constant and Avogadro's number multiplied together here. So what could we do to combine those? What is Kb times Na equal to?
We get the ideal gas constant R.
Yeah, exactly. So we can replace that and just say Kb times Na is R. We've also got a times T and a number of modes and divided by 2. So this is a more compact way of writing the energy for 1 mole of molecules. R times T times number of modes over 2. R being about 8.31 joules per Kelvin mole. And note that the units work out there nicely. The kelvins and kelvins cancel out, so we're left with just the joules per mole from R. And then one last thing, presumably we're not going to be dealing with exactly 1 mole. We could be dealing with any number of moles. So if we're dealing with the whole sample of n moles, we could just take the formula we have so far, R times T times number of modes over 2, and do what with it?
Would it be multiplied by the number of moles you have? So if you have 2 moles, you put,
Exactly.
you multiply that formula by 2?
Yeah, multiply that whole formula by n. So this would be the energy of the whole sample. And we would call this I mean, all of these are thermal energy because we're talking about energy related to the temperature. So this would be a very useful and convenient and compact formula for the thermal energy of the whole sample. Thermal energy of the whole sample is number of moles times ideal gas constant times the temperature of the sample times number of modes per particle divided by 2. So this, I think, is probably one of the most useful formulas for thermal energy, at least as long as you're dealing with some sample where you know how many modes there are. Or alternatively, where you know everything else. Maybe you know the energy and the temperature, and you're trying to find how many modes there are to figure out information about what type of molecule you're dealing with. Any questions on that so far? And as usual, we often don't care about how much energy there is. What we really care about is the change in energy. So if we apply a delta to both sides, what's the only part of the right side that we would expect to be changing? Yeah, probably the temperature. So that means everything else is a constant and can be factored out. We just get n times R times delta T times number of modes over 2. So we can use this as a formula for how much the thermal energy changes. One caveat on that, if you have a sample that, let's say, starts off cold and you make it very hot by adding lots of energy, what else is also going to change?
Bond energy.
Well, let's assume it's a gas the whole time. Let's say you've got cold gas and you add lots of heat and make it a hot gas. What else in this formula might be changing?
Could it be kinetic energy?
Well, kinetic energy is included in here. Thermal energy includes the
Okay.
kinetic energy of the molecules and the rotational kinetic energy, possibly the vibrational potential energy. But what do you know about number of modes of a gas at cold temperatures versus hot temperatures?
They can be frozen out.
Yeah, at cold temperatures, some of the modes might be frozen out. At hotter temperatures, those frozen modes might activate. So if you're talking about a very large change in temperature, it's possible that number of modes itself might change. So in that case, you might end up with delta E thermal equals N times R times delta temperature times number of modes over 2. Something like that. If both the temperature and the number of modes could be changing. So final temperature times final number of modes minus initial temperature times initial number of modes. And I think at that point it gets more complicated because some of the temperature change happens at the lower number of modes and some of the temperature change happens at the higher number of modes. So I don't think it's just going to be a straightforward subtraction in that case, but this would at least give you an approximation. For now, though, let's assume that the number of modes does not change. What we can do with this formula, now that we have a formula for delta E thermal in terms of all these other useful variables, we can substitute this back into our definition of heat capacity in the first place. This formula we can use back here when we were defining heat capacity in the first place. And again, we're assuming this is constant volume so that all the heat goes into changing the thermal energy. Because heat capacity is defined as heat over delta temperature, but as long as the volume doesn't change, we know heat is the same as delta E thermal. If we fill that in, if we just replace delta E thermal with this convenient formula, N times R times delta T times number of modes over 2. And then we also need to divide that whole thing by delta temperature because that's part of the definition of heat capacity. So that's our heat capacity. Heat capacity is the formula we just got for delta E thermal divided by delta temperature. When we simplify that fraction though, what's going to happen?
The delta T's will cancel out each other.
Yeah, exactly. We've got a delta T in the numerator and a delta T in the denominator, so those cancel out. And we're left with CV equals N times R times number of modes over 2. So that's a very convenient formula for the heat capacity of an object. As long as you know the number of modes and how many moles there are, you just multiply number of moles in the substance times ideal gas constant times number of modes per particle divided by 2. So you can use this to predict the heat capacity of, let's say, 5 moles of helium, for instance. Just as an example, let's say you have 5 moles of helium gas at constant volume. How many modes per particle does that have? If it's just helium gas? Yeah, it should be 3, because helium is a noble gas. It's going to be always monoatomic. A monoatomic gas is going to have just the 3 translational kinetic energy modes, and that's it. So if we multiply this out, if we just fill this into the formula, we should expect its constant volume heat capacity to be 5 moles times 8.31 joules per Kelvin mole times 3 moles per particle divided by 2. Moles and moles cancel out, so we get 5 times 8.31 times 1.5 is about 62. 62.3 joules per Kelvin. So that would be the heat capacity of that sample, in the sense that if you have 5 moles of helium gas held at constant volume, like in a rigid walled container with either no piston or a piston locked in place, it would cost 62.3 joules of energy per degree of, or per Kelvin of temperature change. Kelvin or degree Celsius. If you're talking about a change, they're identical. So that should be the heat capacity. Any questions on that so far? Of course, if you want to make a data table of heat capacities of various substances, it wouldn't be useful if you had to list out like heat capacity of 1 mole of helium, heat capacity of 2 moles of helium, heat capacity of 3 moles of helium, and so on. We want to standardize this. What would be a convenient standardized number of moles to use here? What would be the easiest value to use for N? Yeah, let's just standardize this to 1 mole. So if we want to standardize this, let me make some room here. Let's standardize this to 1 mole. And we call this the molar heat capacity. Or sometimes the molar specific heat. That just means the heat capacity of exactly 1 mole. And so we can find that, and it's usually written as C sub Vm. In the sense it's the heat capacity per mole at constant volume. And for that, we would just plug in 1 for N. So we just get 1 times R times number of modes over 2. So it's very easy to calculate or predict what the heat capacity is going to be of exactly 1 mole at constant volume. You just take number of modes, divide by 2, multiply by R. And you could plug in 8.31 for R if you need a numerical value, but this is often just written in terms of R. Like for any ideal gas, number of modes is going to be 3, so 3 halves times R. Or for a diatomic gas with all modes active, you'd have 7 modes, so it would be written as 7 halves times R. So heat capacity at constant volume is always going to be this formula. And that makes it very predictable, very convenient to work with. Any other questions on that, the constant volume heat capacity stuff? Or any other questions or other topics you'd like to work on? I mentioned earlier that if you do allow the volume to change, you could treat that as work leaving the system, like if the volume's expanding and lifting up the piston. Have you seen anything yet about how to calculate how much work there is done, how much work is done there?
We've just learned the negative P by delta V.
Yeah, that should work. That if you have pressure, if you know the gas's pressure and volume, in fact, this ties in very closely to pressure and volume. One thing that's very convenient here, if we go back to this formula we just had for delta E thermal, where else have you seen NR delta T?
Was that, it was the formula was like PV equals nRT or something?
Yeah, if we go back to the ideal gas law, pressure times volume equals number of moles times ideal gas constant times temperature. Or if you apply a delta to both sides, delta, and in this case, pressure and volume could both be changing. Maybe just one is changing, maybe just the other is changing. If they're both changing, this would be thought of as pressure final times volume final minus pressure initial times volume initial. So that's what we mean by delta P times V. The whole final value minus the whole initial value. Or if just one of them is changing, this could be like pressure times delta volume, if only the volume is changing, or delta pressure times volume, if only the pressure is changing. Or delta the whole thing, if they're both changing. But in general, delta pressure times volume. That means, though, we can make a substitution. If we know that NR delta T is delta PV, we can replace that in the formula. And keep in mind, this only works for a gas. The formula we have so far, N times R times delta T times number of modes over 2, that works for any substance in any phase. But if it's a gas, we can make this convenient substitution and say delta E thermal equals delta P times V times number of modes over 2. So this is an alternative formula for delta E thermal that we can use for any ideal gas. And one of the really convenient things about that, we now have a formula for delta E thermal that doesn't have what variable. What variable doesn't show up here anymore at all.
Temperature?
Yeah, we have a formula for delta E thermal that does not require us to know the temperature. You don't have to know the starting and ending temperature. You also you don't need to know how many moles of gas there are. All you need to know is how much pressure it's under and how much space it takes up at the beginning and end. So this can be very convenient because pressure and volume are often values we know for a gas. You can measure, like if you've got a gas in a container, you can measure how much space it takes up geometrically. And if you have a barometer or some other tool like that, you can measure the pressure. So you don't even need to know what temperature it is. All you need to know is the pressure and the volume at the beginning and at the end. And if you also know the number of modes, then you can calculate how much energy it takes to make that change happen. Or alternatively, if you know how much energy was involved and you can measure the pressure and volume, then you can back calculate the number of modes. And that can give you some useful information about the type of gas it is. Like if you know it's some sort of triatomic gas, but you don't know what shape it is, calculating the number of modes can give you an idea of whether it's linear or nonlinear. So you can get information about the shape of the individual molecules just based on how it responds to heat being added to it. Any other questions on that so far? Then let's take a look at what happens if we do allow the volume to change. Specifically, let's assume, I think we have all the information we need over here, delta E thermal over delta T. Yeah, let me clear this out for now. Let's take a look at what happens if the volume is changing, but let's assume the pressure is constant. And conceptually, how would you do that? Like, what would be a way you could set up an experiment or set up a container that allows the gas's volume to change, but makes sure the pressure does not change?
Would a balloon be an example?
Sorry, what was that?
I was about to mention the balloon.
A
We talked
balloon
about it in
almost
lecture
works.
about.
The only
Okay.
problem is if you have, like, let's say you have a balloon and you apply some heat to make it hotter and it also expands. Does that stay at the same pressure the whole time?
It does not. So
Not quite, because you've got, I used to think a balloon was an example. That was usually the example I would list at this point, because you've got the atmospheric pressure pushing in. But the problem with the balloon is that the gas inside the balloon is not only being pushed on by the atmosphere around it, but what else is holding the gas in? What's that gas wrapped up by?
The rubber itself?
Yeah, you've got the rubber or plastic or whatever of the balloon itself. And that has a tension force which is pushing in on the gas. And as the gas expands, the rubber gets more and more stretched. And so you get more tension force pushing inwards. So that's actually not a constant pressure example, because as it expands, the balloon skin exerts more and more pressure because of the increasing tension. It almost works, but not quite. I guess you could say if the balloon is not too stretched out yet, it mostly works. But as the balloon gets more and more stretched, the pressure changes more and more. But if we take a look at how pressure is defined, what does pressure actually mean? When we say that a gas is under a certain amount of pressure, what is pressure? Or if you're applying a certain amount of pressure to something, what does that mean? It's related to force. It's not just the force. It's more about how spread out, how distributed the force is. Like if you're pushing on a wall, for instance, you're applying a certain amount of force, but that force is spread out over what region, what area. It's not all just applied at one point, right? You're spreading out the force over what region? Yeah, specifically not the entire surface of the whole wall, but just the surface of the contact surface, the region where essentially your handprint, where it intersects the wall. So pressure is not just how much force you're applying. Pressure is how spread out the force is, or how concentrated the force is. Pressure, specifically, we define pressure as force over area. That is how much force you're applying divided by how much area it's spread out over. Footprints, I think, are another good example. If you've got two people walking on sand, what determines how deep their footprints are in the sand? Yeah, their weight's going to be a big part of it. That is how much force they're pushing down on the sand with. But so in general, I would expect a heavier person to leave deeper footprints than a lighter person. But what else also matters? If you have two people of the same weight walking on sand, What else is going to make a difference in how deep the footprints are? Right, the area. And yeah, to some extent, the speed of walking as well. If you're running, you're probably going to hit the ground harder than if you're just walking casually. But assuming you've got two people of the same weight walking in the same way, the difference in depth is going to be about the area of the footprint. If you've got somebody in really big floppy clown shoes, they're going to be spreading it out over a much larger area. Whereas if you're in stiletto heels, you're going to be applying it over a much smaller area. So the larger area is going to leave a very shallow footprint because the same force is more spread out. Whereas spike heels are going to leave a much deeper footprint because you've got the same force concentrated in a much smaller area. And this is why we set up the definition this way. Let's say it's the same force, but a smaller area. If you're dividing by a smaller area, you get a larger result, a larger pressure. So a very high pressure might mean lots of force concentrated on a small area. Whereas a weaker pressure would mean less force spread out over a larger area. And this applies very well to gases, because if you have, let's say, a gas in some sort of walled container, the gas is pushing out on the container and the container walls are pushing back in on the gas. That's force spread out over the surface area of the walls and roof and ceiling of the container, or walls and floor and ceiling. So that's what pressure is. In terms of a gas, it's the force that the walls and the gas are exerting on each other divided by the area of that surface, the area it's spread out over. Any questions on that so far? So let's say you have a gas in a container. Let's say a container. And if you want to allow the volume to change, let's say you've just got this gas in the container. If you want to allow the volume of the gas to change, what would you have to include in the container in order to allow the gas to expand or contract?
Maybe a lid, a weighted lid.
Yeah, we specifically want a lid that's able to slide up and down. In other words, a piston. So let's assume we have a piston that's able to slide up and down. So here's our piston. It's able to slide up, allowing the gas to expand, or also to push down, causing the gas to contract. But the thing is, we want to make sure the pressure is constant. The piston allows the gas to expand and contract, but to make sure the pressure is constant, let's say we consider the pressure on the piston. How would you make sure that the pressure of the piston is constant? Yeah, we can apply a force on the piston, and presumably the area of the piston is not changing. The piston is staying a constant size. So to make sure we get constant pressure, we need to make absolutely sure the force is constant. And what would be an easy way to design this to make sure the piston experiences a constant force? What's a naturally occurring force that's very easy to make constant? Yeah, gravity is probably going to be the easiest one to use. We have gravity all around us. We may as well take advantage of it. If you just make this piston heavy, a weighted piston, that heavy piston is applying a constant force, just the force of its own weight on the gas. So you notice that you're not pushing or pulling on this piston at all. You're just letting gravity do the work. So if you have just this piston that's just sitting there, how would you make this gas expand, for instance? You can't pull on the piston because that would be applying extra force. But how would you make the gas expand? Yeah, you can add heat. Maybe put this over a burner. Let's say we just have fire lit under it. Pretend that is very well drawn fire. We just put this over a burner, add some heat. That's going to increase the temperature of the gas and also make it expand, causing the piston to rise. So adding heat causes the gas to expand, which causes the piston to rise. But as the piston rises, it's gaining potential energy of gravity, which means the gas is doing work on the piston. So we can treat that as heat entering the system and also work leaves the system in the sense that the gas is doing work to lift the piston up. So that's what's going on here. Heat entering the system and work leaving the system. And how do we calculate how much work?
For work is a pressure, negative pressure times delta volume.
Yeah. Negative pressure times delta volume. And we can use this formula because pressure is not changing. If the pressure and volume are both changing, this formula doesn't work. You can still use average pressure times change in volume as an approximation. But formally, this formula only works if the pressure does not change. Like if you have this weighted piston and you're not pushing or pulling on it any further. The reason this works ultimately, if we substitute the formula for pressure here, pressure is force over area and multiplied by change in volume. We can rearrange this a little bit and write it as force times change in volume over area. And think back to geometry. What happens if you take a volume and divide by an area? What would you get? If you consider this region geometrically, like so let's say the piston went from here up to here. Let's see if I can draw this in 3D. If we have, like, let's say we know the initial location of the piston. Let's say the piston started off here and the piston rises up to here. The amount of volume we've just covered is this region right here, sort of a cylindrical shape. Think back to geometry. How would you calculate the volume of that cylindrical shape?
4/3 pi r squared.
Sorry, what was that?
Is that the 4/3 pi r squared?
I think that's for a sphere. For a cylinder.
Oh, right.
Is it the area of a circle times the height, essentially? Because it's
exactly. Area times height. The area of the base. And note that the base doesn't necessarily have to be a circle. No matter what shape the cross-section is, as long as it's a consistent cross-section, you can just take that cross-sectional base area and multiply by the height. That'll tell you how much volume that shape traces out. Because you could think of this as, like if you just imagine this as this shape of the base moves, and as it moves, it traces out this region of space. The area, the volume of that region of space is the area of that shape that's moving times the distance it travels. So that's really what this formula means. And I mean, this is how I interpret it. You've got, yeah, a stack of CDs. That's a good way to think of it. If you've got one CD that takes up a certain tiny amount of space, times the number of CDs tells you the total amount of space it takes up. And that's a discrete case rather than a continuous case, but it's the same idea. You take the cross-sectional area times how much it's traveling to trace out that shape. And that tells you the volume. But that also means if you take that volume, area times height, and divide by area, what's left? What happens when we take this formula and divide it by area? Yeah, we're left with just height. Or since we're talking about change in volume, that becomes force times change in height. Let's say delta y. So the pressure times change in volume works out to the same thing as force times change in distance or change in position. And what do we call force times distance traveled? You apply a force to a moving object and the force times distance tells you what? What were we trying to calculate here in the first place? Yeah, this is the definition of work. Work is defined as force times distance, how much force you're applying to the object times how far it moves while you're applying that force. So the reason pressure times delta volume is valid in the first place as a formula for work is because if you work through the geometry and algebra, you get force times distance anyway. So force times distance is the definition of work. Pressure times change in volume also happens to work out to the same thing if pressure remains constant. So in any situation where you've got a gas that's changing volume while the pressure stays constant, pressure times change in volume is valid as a formula for work. And that's often more convenient because pressure and volume are usually easier to measure for the gas than the force it's exerting on the piston and the distance the piston moves. It turns out this is even valid if you've got like several walls expanding in several directions. Force and distance would be difficult to calculate in that case, but pressure times volume or pressure times change in volume still is valid for calculating work. And the negative sign here is really all about direction. For instance, in this case, the volume's expanding. So what's the sign on delta V? If the volume's expanding, yeah, delta V is going to be a positive number, greater than 0. But as the volume expands, would you say work is entering the system or leaving the system? Would you say the piston is doing work on the gas or the gas is doing work on the piston? Yeah, I'd call that leaving. As the gas expands, the gas is doing work to lift the piston up. The gas is causing the piston to gain potential energy of gravity. So that means the gas is losing energy to cause the piston to gain energy. So I'd say work is leaving the system, leaving the gas. And if work is leaving the gas, we treat that as a negative amount of work. So delta volume and work will have opposite signs. If the volume is increasing, then work is leaving the system, and we call that a negative amount of work. Whereas if the volume is shrinking, like let's say you allow the gas to shrink, the piston is pushing down, the piston is doing work to the gas. So that would mean work is entering the system. So if volume is decreasing, then work is positive. So in general, work and delta volume will have opposite signs. And that's ultimately why we need the negative in the formula here. Work is negative pressure times delta volume. That guarantees that work and delta volume will have opposite signs. Any questions on that so far? So if we go back to the idea of heat capacity, we can still define heat capacity as heat over delta temperature. But if the pressure is constant, then we can no longer use the previous idea that heat is the same as delta E thermal. Because delta E thermal is being changed not just by heat here, but also by what else? What other transfer of energy do we have to consider? Yeah, heat and work. But now we know how much work is done. We can replace work. So we've got delta E thermal changed by the heat we're adding to the system by putting it over the flame, and the work leaving the system as the gas expands and pushes up the piston. But we now have a formula for that. We can replace delta E thermal with heat plus negative P delta V. That's the amount of work done in this constant pressure situation. We want to have something we can substitute in for Q. So how would you isolate Q here? How would you solve this for just heat?
Would it just be delta E thermal minus parentheses work?
Yeah, delta E thermal minus work. And since work is negative P delta V, we could also think of this as adding P delta V to both sides. So this is what we can do for heat here. Heat is change in E thermal plus P delta V. That is delta E thermal minus work. So we can substitute that whole thing in for heat in the definition and end up with Cp, that is the constant pressure heat capacity, is delta E thermal plus P delta V divided by delta temperature. We could then split that up. The divided by delta T can distribute to both of these terms. So we get delta E thermal over delta T plus P times delta V over delta T. So that's the, that could be used as a formula for heat capacity at constant pressure. And we can go a little further here. For example, where else have you seen delta E thermal over delta T? Where else did we just see that? Yeah, that's exactly CV, delta E thermal over delta T. So that means Cp is Cv plus this extra term. In the sense that at constant volume, it's easy to change the heat. At constant pressure, it's more difficult. It takes that amount of heat plus some extra heat to account for the expansion, the energy lost due to that expansion. And one other convenient thing we can do, we can replace P delta V with the ideal gas formula. P delta V is the same as NR delta T from the ideal gas formula, ideal gas law. And when we simplify that, what's going to happen? What happens when we divide those in that fraction?
Delta T's will cancel each other.
Yeah, the delta T's cancel out, so we now know how much more. We can say constant pressure heat capacity is a little bit more than the constant volume heat capacity, and the little bit more is just number of moles times R. Or if we standardize to exactly 1 mole, that's just 1 times R. So at constant volume, the constant volume molar heat capacity plus R tells you the constant pressure molar heat capacity. So that's how those two different heat capacities are related. And that should be true for any gas. For any gas, any ideal gas, the constant pressure molar heat capacity is exactly ideal gas constant more than the constant volume molar heat capacity. Any other questions on that? All right, you're welcome. I will see you next time.